And then the lionfish is a classic invasive species happening right in our backyard. There's also problems with coastal development, eutrophication and sedimentation, so pollution, building up the coastline, coastal runoff that's causing a lot of problems because of agriculture or mining in Australia especially. And then just pollution that's coming off of the land into the ocean. And then lastly, the kind of global issue of rising temperatures and ocean acidification. So all of these factors are turning really healthy environments into degraded environments. Now we've already seen dramatic changes happening. So within the Caribbean, in the 1970s, coral cover was quite high. It was a really beautiful place. In present day, coral cover has declined by 80 to 90% there. So this is a figure that's showing coral cover in the 1970s as pretty high, and then now today it's really, really low. The Indo-Pacific isn't going to be quite as dramatic as the Caribbean, but it's still declining. So in this study, they surveyed 6,000 surveys on over 2,500 reefs. And coral cover in the early 80s that's the little star thing is at the mean coral cover, was at about 42% in the Indo-Pacific. So these graphs are grouped in the early 80s to 2003 for each kind of pair of sets. The top figure B and C are the ones that are for the entire Indo-Pacific region. Now, if you look at the average coral cover after the 80s, in 2003, it had declined by about 50%, was at 21%. Now, that's a decline of about 1% per year, but in the last 7 years, it was much higher. Okay. So with this data, we know that the percent of mean coral cover has declined. And because of that, you know that there are more degraded reefs now. So instead of having more healthy reefs than degraded, you have more degraded. So if you compare the top part of the red box to the bottom part, there's significantly more degraded, unhealthy reefs with low coral cover compared to what there used to be. And the amount of healthy reefs, so there were more healthy reefs in the 80s, and now in the 2000s, there's a lot less. And the solution that's been proposed is that we set up marine protected areas. These are one of the only methods that we have in the marine system to protect marine environments. That and just closing certain size classes to fishing pressure. And the basic principle behind marine protected areas is that by closing a reef and not allowing certain activities to happen, you're going to save that reef, but those reefs are also going to rescue some of these degraded habitats. And that's pretty much one of the only ways that we have to kind of save the ocean, really. So the problem is now we have very few good reefs that need to save all of these bad reefs that are degraded. And we don't really know if that's going to work. Now the idea behind the marine protected area, like I said, is you have a hypothetical reef here. You put some kind of border, mark it in some way, and you exclude something. So in the Great Barrier Reef, there's like 17 different types of marine protected areas where it's all the way from everyone's excluded to scientists are allowed to, you can't fish with only a spear gun, or you can't fish with hook and line, or whatever. But either way, you have some kind of way that the area is protected from some kind of effect. Say you just close it completely. Now, what you're asking things to happen is you want the larvae that are produced in the marine protected area to be produced. The fish in there will grow bigger and have more larvae. Those larvae go off into the pelagic ocean, and that's where they develop. So they spend about, depending on weeks to months, in the open ocean where they develop into a fish. And then they need to seed the non-protected area, because this area is going to be producing more larvae than this one, because these fish are bigger and there's more of them. So they need to come over to this degraded site, or the non-protected site, and help supplement the amount that we're taking out through fishing pressure. Some of them will obviously come back into the marine protected area. So that's called seeding. And then the other way that marine protected areas work is when just adult fish move over, and that's just called spillover. Now I'm going to show you a video from here. So this is Fiji, a picture of Fiji where I did a lot of this research. I worked on the island of Vitilevu, like right along the southern coast right here. And this is a close-up map of it. And this is a really unique location because you have really healthy reefs next to really degraded reefs. And the reason they are that way is because the locals have done this like grassroots movement to set up their own marine protected area. So they're not actually protected areas in a legal sense. It's just that the villages have kind of gone together and decided to make these areas protected. And if someone's caught fishing in them, they'll beat them with a 2x4. It's not illegal to fish there, but the villages make it very well known that you should not do that. So we worked in 3 replicate villages right along the coast. Otua is where I actually lived at, but in the white bars is the marine protected area, and in the yellow area is the places where the people fish. And they fish quite heavily because this is their main source of protein. I'm going to show you a video taken at these 2 red dots. They are in Otua, obviously. So this is taken in the marine protected area. You can see a high coral cover, there's very low algal cover. So this is a really, really healthy reef. There are a lot of fish in here. I think they were just scared of me when I was videotaping. You'll see some in a little bit. But you can see a lot of fish. There's not a lot of algae, there's a lot of coral. There's a lot of topographic complexity, so the fish have a lot of places to hide. This is just less than 500 meters away in the non-protected area. So there's almost no coral anymore. It's a lot of algal beds. This is a blooming algae called sargassum. There's very few fish species. There are some fish here, but not as many. The topographically complex area is now flattened because of all this this is all coral rubble, so it's no longer even coral. So the fish lose their place to hide, and the species have changed. And this is like 500 meters away. So when you're actually swimming there and you go from one area to the next, you can see that you've crossed out of the marine protected area just by how the reef looks, because it's so dramatic. And this isn't specific to Otua. All of the villages that we work in look very much like this, where this drastic change between healthy and degraded habitats. So now really the question that we're trying to ask is, are these marine protected areas working? So the first thing they have to do is protect the species within inside their borders, let them grow bigger, let them have more offspring, which they definitely are doing that, because you can see that there's more fish there. The fish there are bigger. We've done surveys on that. The coral is healthier. So it is doing its job in that it's protecting what's there. But now, is it doing its job in allowing spillover to happen, or allowing the marine protected area to seed the non-protected area? And what you're really asking is, are larvae produced from this healthy reef going to go off into the pelagic environment and actually see that non-protected area as a reef at all? And since, as I talked about before, habitat selection is such an important quality in fish, and it's an important decision, they should be selecting the best quality habitat, and they should have evolved to find the best quality habitat right away, since they don't move very far. So these marine protected areas may not be as effective as we think if the larvae are actually rejecting this behaviorally. Now, one of the reasons why coral reef fish are really interesting in doing this kind of work is that you have a relatively sedentary adult, so they move only about 5 meters from where they initially settle, and they give rise to this highly dispersal larval phase. The larval can be in the planktonic environment for weeks to months. We don't know a lot about the larval phase. It's kind of the black box in marine connectivity research. They're often really, really small, they're clear, they're really hard to catch, especially early on. So we don't really know what happens at the larval stage very, very much. But we do know that they have to go off into the open ocean with very little experience on them in the reef itself, and then come back and find a good reef. The other thing that makes coral reef fish even more interesting is coral actually only accounts for about 1/100th of a percent of the ocean's surface area. And so you're actually asking these tiny, tiny little fish to find like a needle in a haystack, because they have to locate these reefs. So their ability to find settlement sites should be really, really strong. The other thing that you have in coral reefs are fish like the anemone fish, where not only do they need to find a reef, but they need to find a reef that actually supports their species-specific anemone. So, like, this is the Nemo clownfish, Hercula, and it only actually lives in 3 different anemone species. So not only does it need to find a good reef, it has to find one that actually has one of those 3 anemones on it for it to actually live. So you have these super specialist species that are living on the reefs and having to find this really particular habitat. Other fish that I like to point out is the pygmy seahorse. So the seahorse is actually right in the middle of that circle, and it's evolved to look just like the Gorgonian sea fan. The seahorse is only, as an adult, about the size of my pinky fingernail, but if it doesn't find the right sea fan, it's not going to live. So their habitat selection abilities have to be really, really high. Now, one of the ways that larvae may be able to find their reefs is using sensory mechanisms. So when they're off in the pelagic environment, you'd assume that it's pretty much featureless. So it's vast blue ocean, there's no bottom, there's nothing to like orient themselves around except for sensory cues. We do know that they use sound, sight, and smell, and then some compass and magnets are also starting to be explored on more. But what senses they use are pretty unknown, and at what scales they use these senses, so it's definitely unlikely that the larvae are going to use visual cues when they're off in the open ocean because there's just nothing to see. But whether they're using sound first and then chemical cues after that is pretty unknown. It's likely that they're using as much information as they can. Now, I work on chemical cues, and one of the important things about chemical cues is it actually provides information on the habitat itself. So you'd expect a coral reef to smell like coral, you'd expect a seagrass bed to smell like seagrass, and so on. So you can get information from the chemical cues on just habitat quality. Most marine fish actually hatch with a really well-developed olfactory system. So this is a 1-day-old clownfish, that same species that was in the picture. And you can see from the microscope picture is that their olfactory system is actually fully functioning at the time of hatching. So this is the nose, and this is the inflow and the outflow, and this is it close up again, the inflow and the outflow. And when the olfactory system isn't fully developed, this skin flap over the top won't be there. But in most coral reef fish, they actually hatch with this system ready, which implies that it's probably really useful initially right away when you start their lives. Now the other thing that chemical cues provide that most other cues don't is a history. So if you're trying to locate a habitat and you want to avoid places with high predator pressure, you can't see that a predator used to be there, but oftentimes you can smell that a predator used to be there, since many predators are sit-and-wait predators and they'll leave a chemical kind of halo where they've been. Chemical cues have already been found to be really important in microhabitat recognition, so we know that fish can tell the difference between their conspecifics and congenerics just through smell alone. We know that coral reef fish can tell the difference between live coral tissue of different coral species or coral tissue versus anemone tissue, something like that. So we know at like a really microhabitat scale when they're choosing within the reef where to go, they do use chemical cues for that. And more recently, we found that settlement stage larvae can actually discriminate between a reef that they were taken off of and a reef nearby within a 10-kilometer radius. And these reefs that were compared in this study were actually, to a researcher, were very, very similar. So there was no difference in coral cover, there wasn't a really difference in species composition, but the fish could tell with chemical cues alone which reef was which. So this really implies that maybe chemical cues are more important than just microhabitat recognition, and they can be used for a much broader scale. Now, one of the ways that I test chemical cue preference is I use a 2-channel choice flume or an Actima flume, and pretty much using flow meters and dye tests, 2 water sources are delivered into the flume. And because the water sources are flowing at the same rate, they don't mix, and I test for that with dye tests so that there's no areas of turbulence or eddies. A fish is placed in the flume, and then it's allowed to acclimate for 2 minutes or habituate to its surroundings. Then it gets a 2-minute test period where every 5 seconds I take and record its position if it's on the right or the left side. And then everything is switched. And the reason that we switch it is to show that the fish isn't showing some side preference, that it's actually following the cue to the other side. So the blue becomes green and the green becomes blue, and then we watch the fish's behavior again. Just to show you how this works, so this is a video of a butterfly fish larvae, and fish have really strong predator recognition. So on the opposite side of the flume is water that's had a predator soaked in it, and this side of the flume is water that's had just plain seawater. You can see the butterfly fish is staying in the non-predator side. It goes in the predator side for just a second and then scoots back over to the non-predator side. The trials just continue like that. So that's just an example of how it works. So going back to Fiji and back to the initial question of is habitat quality, can they tell the difference between that healthy reef and the degraded reef from the video just from chemical cues alone? This is data from Botua, so where the video was taken. And there's a damselfish, a parrotfish, and a wrasse. So that's a planktivore, an herbivore, and a predator. So different trophic groups, different types of fish, different sizes of, they're all juveniles that I tested with, different sizes as adults. And I collected the fish from either the healthy reef or the degraded reef. And I gave them the choice of water from the healthy reef or the degraded reef. Now, when they're in that flume, if they prefer a water cue, they would spend more time in that. So that blue line is about at 50%. So any bars that are above that blue line, they prefer the cue. Any bars that are below the blue line, they're avoiding the cue. And this is the data just from Botua. So it's an N of 20, and you can see that regardless of where the fish were collected from, if they were collected from the healthy reef or the degraded reef, they prefer the smell of the healthy reef. One of the reasons why we had to run this test this way is because in Fiji you can't get light traps, you can't catch naive fish. So because the fish had already had some experience on the reefs, I wanted to make sure that their cue preference weren't a reflection of where they had been, rather they were their preference. And this clearly shows that even if you were from the non-MPA, you still prefer the MPA cue. Now, just to show that this wasn't just some weird fluke, and I happened to pick the 3 right fish from Botua, which is the area that smelled the most different. This is data that's been pooled, so we have all the fish from the non-MPA of Botua, Lili, and Honda, so 3 different villages, and all the fish collected from the MPAs of those same villages. And there's 15 fish species here. So the blue ones are all damselfish, which are going to be the planktivores. The yellow ones are butterfly fish, which are corallivores. And then you have 5 different species of herbivores and 2 predators. And you can see from this that regardless of where the fish were from, regardless of their species, their trophic group, anything like that, they prefer the smell of the MPA over the non-MPA. Each of these bars is 60 fish, so there's quite a big sample size, and which explains the very low error that's shown. But you can see that they have really, really strong preferences. So now we know that the fish can tell the difference between the healthy and the degraded reef, but what would make the healthy reef smell differently from the degraded? And one of our ideas was it could be the large amount of seaweed in the fish reefs, it could be the large amount of coral in the healthy reefs, or it could be a combination of both, so like a double-edged sword. So in order to test for this, I took water from the healthy reef and compared it against water from the healthy reef with the chemical cues of seaweed added into it. And these are the same fish species as we had before, and it's the same pooling where all the reefs are combined because there was no significant difference. But you can tell that when you add the chemical cues of seaweed to the healthy reef, it makes the healthy reef more repellent. So seaweeds are definitely something that fish are cueing in on and avoiding. If they weren't avoiding the seaweeds, you'd expect 50% of them to spend in either water source because they're essentially the same without the seaweeds added. So to see how coral is affected, we basically did the same test except flipped. So we took the degraded reef water and tested it against the degraded reef water with coral. So if coral didn't matter to them, you'd expect them to spend the same amount of time in either reef or in either water type, and that's not what we show. So when coral is added to the degraded reef, it's much more attractive than when coral is not there. And it actually does matter what you're looking at. So we tried to see is all algae a bad thing, or are they specific to certain types of algae? And they do have certain preferences. So in this first graph right here, we have chlorodesmus, which is it's sometimes called mermaid's hair or turtleweed, and it's an algae that doesn't bloom. It's chemically toxic, but it's found in healthy reefs in small quantities. And we compared that to sargassum, and sargassum was one of the algae in that video that you see in these huge blooms. And the fish can tell the difference between the chlorodesmus chemical cues versus the sargassum, and they prefer that actually toxic algae that's found in low abundances compared to the blooming algae that's not toxic. And then we did it again with hypnea, which is the same. It's found in healthy reefs, but in really low quantities, versus turbinaria, which is it tends to bloom in a degraded habitat. And they can tell the difference between those two and prefer the non-blooming, low abundance algae over the blooming, kind of high abundance algae. Now, all coral isn't treated the same either. So in this top figure, figure A, we looked at acropora versus porites. Acropora is a really threat-sensitive coral. So it's the coral that will bleach first. It gets eaten by crown of thorns. It tends to degrade really fast. And it's actually the coral that builds a lot of that reef structure. So it makes a reef more topographically complex. And we compared that to the chemical cues of porites. And porites is really a hardy coral. It still branches, but it's much more hardy. And they prefer the smell of the threat-sensitive acropora to the hardy porites. We also compared acropora to pocillopora. Pocillopora is a weedy coral, so it does get, in a time when the reef is damaged or degraded, pocillopora will die, but it comes back really fast. So you can often find pocillopora growing on like ropes to a boat or a boat ramp or something like that, because it's just a really weedy coral. And they can tell the difference between a weedy versus a threat-sensitive coral. And we think that's likely because if a reef smells like a threat-sensitive coral, then it should be healthy, because it means it hasn't been degraded, it hasn't had a bleaching event, it hasn't had a massive crown of thorns outbreak if acropora is there. So it's kind of the canary in the coal mine. If a reef smells like acropora, it should be a good place to go. Now, coral aren't the only thing found on a coral reef that are important, or fish aren't the only thing found on a coral reef that are important. The coral actually is really important as well. And coral have to make the same settlement decisions as fish. So coral, one day a year, on like 3 days after the full moon, will all do this mass synchronous spawning event. So this is one coral getting ready to spawn. Here's the egg and sperm bundles being released. And then there it is again. So this only happens one day a year. The egg and sperm mix up in the top of the water. They go off in the open ocean. And then these little coral larvae have to find their way to a reef. Now, coral larvae actually are more like more reef organisms where they don't have a face, they don't have anything. They have little cilia that beat around. And they are able to respond to chemical cues and to sound as well. So this is a picture of an acropora coral larvae. And I tested the coral larvae in the same way as I tested the fish. So in the same plume with water flow that was much lower so the coral could actually swim against it. And the coral is actually in that little blue box. So it was much harder to do this just because seeing them was harder, but it worked really well. So if I take coral and give them the same choices of the water from the healthy reef versus the water from the degraded reef, you can see that all of the coral species that I had spawn in little baby pools in Fiji preferred the water from the healthy versus the water from the degraded. So they're making the same preferences as the fish. I asked the coral a number of other questions with that flume, and so this is the figure that I just showed you actually. But if you get down to it, corals basically behave, they have a behavioral preference pre-settlement, which this is the first time that coral have ever been treated in this way. Most of the time, coral settlement sites are just, they inject coral onto a plate and see where it kind of crawls around to. This is asking coral to make decisions when they're still in the ocean phase. Corals' chemically cued behavior match those of the fish, so they prefer the MPA over the non-MPA. They prefer the smell of their conspecific over congeneric, so they like the reefs that smell more like themselves than like different reefs. They prefer a mixed coral species versus a conspecific, so they'd rather be in a reef that's more diverse than a reef that smells just like them. And crustose coral and algae is known to be a really important cue in coral settlement, but the MPA is not unattractive. The non-MPA is not unattractive because of a lack of crustose coral and algae. So when I add crustose coral and algae to the water from the non-MPA, and test it against MPA water, the MPA water is still more attractive. So that's this trial here. MPA was 74% of their time was spent there. Non-MPA plus crustose coral and algae only accounted for 26% of their time, which means that the non-MPA is not unattractive because it's just missing one cue. It has to be a much deeper problem. So that was all laboratory data, and we wanted to see if any of these patterns were actually found in the wild. In a choice plume, you're basically giving an animal a yes/no choice. So you get these really clear, distinct answers when you only have two options. But I wanted to see what the patterns in the wild were. So I ran a series of belt transects. And first, talking about the fish, I looked at the 3 different villages, and I counted the number of recruits along a belt transect. I counted the species of recruits that I found, and then the number of recruit predators. And we found that there were 6 to 8-fold more recruits in the MPAs versus the non-MPAs, and that's despite having 3 times more predators. So the fish in the MPAs aren't there because it's some kind of predator refuge. There actually is more predators there. They're there because they're choosing to. Now it was a little bit harder to find the coral, so I set up these 18 2x2 meter plots, and I had them in the MPA and the non-MPA of all 3 villages. I had half of them, I weeded the algae and I pulled the algae off because I was thinking maybe the corals aren't there because the algae there's not enough bottom surface for them to actually settle onto. And then I also put these tile arrays up. So corals really like to settle on tile, and just in case the algae was leaving some kind of film on the bottom, we put these tile arrays up next to some of the plots to see if they would settle on those plates. So if they're settling on the plates, it means the larvae are coming through the non-MPA, but they're just not settling there. And after 9 months, so this is what it looked like. After 9 months in the village had no significant difference, so all the villages were basically the same. Algal removal had no significant difference, which was really disappointing because it is not an easy job to weed the ocean for 9 months, especially in that non-MPA, which is complete seaweed. So that just made me more sad because it was a lot of work. But in the MPAs, there was a difference that was found. So coral larvae actually settled on the natural benthos of the reef, and they never settled on those elevated tiles. In the non-MPA though, corals only settled on those elevated tiles, and I never found a coral on the benthic, on the natural benthos. So there was a really different contrast with that, and you almost never get this in ecology data, which where only and never are pretty much never used. So that was exciting. So thus far, we know that chemical cues are really indicative of reef health. We know that there's a 6 to 9-fold bias to the healthy habitat based on chemical cues, and that follows with a 6 to 9-fold recruitment into the MPA despite having more predators. So MPAs, or what you really could think of these reefs as healthy reefs, may not be seeding these degraded reefs as we're anticipating. So maybe MPAs aren't doing the job that we think they are, and we need to rethink that part of it. But not only are the habitats of the reefs changing, the habitats of the shoreline are also changing as well. So this is a picture from southern Georgia with like Tybee Island-ish area. And you can see there's salt marsh, and they're quickly turning into this, where people are developing right on the shoreline. Humans love to live right on the coast. So this coastal development could also be a problem for coral reefs. So the rest of the study was done in Papua New Guinea and Kimby Bay, so right up there in the white box. And I wanted to see how terrestrial signals were possibly influencing the marine environment, because if you remember from before, a lot of the things we're doing involves chemical runoff and pollutants and things just washing into the water. So that could be affecting the chemical cues even up on land. Now, what I did at Kimby Island is I had a number of reefs. Kimby Island obviously is an island. Kapapa Island and Tuari Island are both islands. May Reef and Margaret's Reef are just reefs, so there's no terrestrial cues there because it's just a reef in the middle of the ocean. And I wanted to see if fish could tell the difference between between an island reef versus a reef with no island. And a number of fish actually are found only around these island habitats. So this is the data for a number of fish species. Again, this is Papua New Guinea, so the species are a little bit different than before. But this is reef water from an island versus offshore reef water. So two different reefs, but one's coming from right in an island and one's coming from the offshore. And you can see that they prefer the smell of the reef with the island versus the reefs that are offshore. And these are all island-associated reefs. So the island may be, something about the island may be helping them to find the reef. And if I take beach water versus reef crest water from these island reefs, they can tell the difference and they prefer the water from the beach. So something about that island is really signaling that there's an island reef there. And one of the ideas was that it could be the terrestrial vegetation. So this is one of the islands in Papua New Guinea. And you can see that the leaves kind of make a slick off the island, which could be kind of a path for the larvae to find their way to these island reefs that they're associated with. I should mention that the reefs that that a number of fish I tested are not island-associated fish, and they're found on either reef, and they show no preference for the beach water or the offshore water or the reef crest water. So they don't really have a preference, but they're not specific to these island locations. So what I wanted to do is test if the leaf litter from the island could potentially be impacting their behavioral choices. And this is data from the tropical plants. I took native tropical plant water. These are pictures from the different reefs that I worked on. So you can see the leaf litter actually hangs right, this is coral reef right here. The trees are just hanging right over it. And all of the fish species that are island associated prefer the smell of offshore water treated with native terrestrial plant leaf hue compared to offshore water without the leaf hue. So the leaf litter seems to be doing something that's cueing them in on the island habitat. Now, so this is just native leaf water versus compared to non-offshore water with no leaves in it. And this graph is a little bit different because I don't have the opposite bar, but basically 100 minus what this bar is how much time is spent in the offshore water. And when you think about island habitats, a lot of our human disturbances are happening there. So we really like to vacation on islands. People like to go to Fiji and like to go to Florida to go on vacation. And the native plants are what's getting cut down and replaced for agriculture activity or for buildings. Now, one of the main agriculture activities happening in the Indo-Pacific are coconut farms. So you'll see, especially in Papua New Guinea, you'll have an entire offshore island that they've just clear cut all the native vegetation and they put tons and tons of coconut trees, and that's where they farm the coconuts. But you can see that the fish, when given the choice of coconut leaves in offshore water, don't prefer it. They actually avoid the cues of the coconut leaves compared to just plain offshore water. So it's actually an avoidance happening there. One of the other problems with terrestrial systems are sugarcane. So in the Indo-Pacific, there's quite heavy sugarcane farming happening right on the coast. Fish actually avoid the cues of sugarcane even more than they avoid coconut. And then mahogany in Fiji, mahogany is a massive problem. A lot of the mahogany is not native to Fiji, but it grows really well there. So mahogany farms are going to the local villages and saying, hey, we'll build you a school if you let us completely tear down your rainforest and plant mahogany, and you'll still be able to farm underneath the mahogany. So people are agreeing to it. The problem is mahogany have really acidic leaves, and they have a lot of tannins in their leaves, which cause the soil to be unfarmable. So these villages are not only losing their farming locations that they normally do farm under the native plants, but the chemical cues coming off of mahogany is really, really negative towards the fish that are important for them to eat as well. The last thing I did was oil palm. Oil palm is quite famous for orangutan problems where you have massive oil palms replacing places in Borneo and things. But Papua New Guinea is quickly turning into an oil palm plantation, the whole kind of country, unfortunately. And oil palm also is really negatively preferred from the fish compared to non-oil palm water, or just offshore the conclusions from this overall arching study is that terrestrial cues are really important for settlement site selection. Coastal organisms do use native terrestrial signals as a cue, and that's most likely because it would increase the size of the island. So if you think about the island, the amount of chemical cues that an island can export from the coral that's stuck on the bottom is going to be much smaller than the amount of cues that an island can export when you have leaves that are being traveled off the island. So it makes kind of a halo effect, making the island appear bigger and easier to find. And changing these terrestrial signals could be affecting the recruitment patterns that we're seeing. Now, current management strategies may be falling short, and you can tell that from just the first part of the study, where the healthy reefs are being strongly preferred compared to the degraded reefs. So the seeding in the marine system may not be working, but also we currently don't really integrate our management strategies. So shorelines are pretty much managed completely separate from the ocean that's right in front of them, and we may need to start integrating the management to include the shoreline with the coastal ocean system, because those shoreline chemical cues could be equally as important as some of the cues just coming right from the water. With that, I can take any questions. That's pretty much it. Any questions? Yeah.
So tying us back to how you said the hope is that the non-degraded reefs would help kind of resuscitate the degraded reefs. I guess maybe I missed the wrap up there. Is that supported by what you found? So it looked like these the preference was to go back to the non-degraded ones. So what's going to happen to the already degraded? Is there any rescue potential there?
So I think that's kind of our next step in the research. So we've just finished doing a study looking at a dilution experiment to see just how, because in Fiji these reefs are so drastically different. Like, actually, what is the cutoff that makes a reef unattractive versus attractive? And they can tell it's a degraded reef pretty easily. But one of the things that I'm hoping to do next is to go back there and outplant some of the corals that are deemed like the most attractive, and remove some of the seaweeds, and seeing if we can change the chemical signature coming off of those degraded habitats. Maybe then the fish will start coming back. And right now it's kind of a negative death spiral where the reef doesn't smell like the right thing, so the fish don't go there, which makes more algae come because there's nothing to eat the algae, and then less coral go there because there's no space for the coral. But if we could somehow flip that, the idea is, obviously more research needs to happen, is that we would be able to have nature kind of work for us rather than against us. And if we can change the chemical signature coming off the reef, you may be able to start reversing that, where if you can find the right mix of coral and the right removal of algae, you can get the right herbivores to come in, they can start eating the algae, and then that could start to reverse the problem. I guess really the kind of overarching thing from this study was just that what we're doing is probably not effective and not working in the way we want it to, and we need to start doing other things. How to do those other things we're still not really sure of. So for the terrestrial management component, it may be something where they could have a buffer of a certain distance of the shoreline is native plants, and then behind it could be oil palm, mahogany, whatever you want. Or mangroves could be really, really important in filtering some of those chemical cues out of the water so that the coral reef still gets the right cues for fish to come back to. That's still kind of the next step in research. So I think there's a lot of potential to kind of change marine conservation so that it's actually more effective. But right now, I think our idea of, let's just put an MPA here and it'll fix itself is just not working. In some places it does work, and in those places, there's places in Australia where we've done work where you can compare the MPA to the non-MPA, and fish from the non-MPA are produced from the MPA, so they are moving over. But those places often aren't so different from each other, they look really similar. So it's kind of the next step is to figure out at what point does an non-MPA become less attractive than a non-MPA? Like where is that in the spectrum of chemical cues? What chemical cues are they? And then how can we manipulate that to kind of shift things around? So I guess I don't really have the answer to that question, but I have a hypothetical idea behind it. Yeah.
Any other questions?
Yeah.
I guess it's somewhat a generic question. When you go on vacation and they offer, tourists chance to go to the coral reef, what do you recommend? Should you not go there at all? And if you do go there, what are the best practices not to disturb the coral?
So I think, I mean, I think it's really good when people go on vacation and see coral reefs because a lot of people don't know anything about them. And really, once you've seen them in real life, you're just like blown away by it. I mean, videos and stuff don't really do it as much justice as seeing it in person. It's really that people need to be careful. Like corals look like rocks and feel like rocks, but they are alive. So don't stand on them. Don't break them. Don't use them as to hold on to things. Like they are not, rock climbing things. Like you shouldn't be touching them at all. There's kind of a controversy, especially in Australia, that's kind of erupted, is that a lot of these companies take these massive boats out to these reefs and they have these platforms there and they just pump out tourists onto these reefs. And those reefs have really high disease rates and they degrade really fast. And one of my friends did a study and it's probably a result of the sunscreen people are wearing and how much they're peeing in the water is actually causing all these problems for the coral. And there's places in Mexico now where they've banned certain sunscreens and they make you wear this, one of the banana boat, like eco-friendly ones, because they found that actually is less damaging to the coral. So there's even small stuff like that people can do. But then it's kind of a question of, is it better to go on those platform boats where only one reef is getting super hit hard versus spreading out onto some of the nicer reefs? So I think it's good when people still go see the corals. I just think, if you wear a wetsuit instead of just going your swimsuit, then you don't need sunscreen at all. And you can just put it on your hands and on your face rather than coat your body in it and get in the water. Or, and then just being confident to be able to swim in a snorkel setting. That's harder to most people if they're not confident in swimming already, to be able to lay flat and keep your head down and breathe. People like to swim like that instead of being flat on the surface. So I think if that is like practice more in a pool or something, that could really be helpful. But certain dive companies really push eco-friendly tourism versus not, and it's pretty easy to tell the ones that are going to be more sustainable than the ones that aren't. And it's more enjoyable when you go on one of those dives because they usually don't take out as many people. They usually a portion of your money goes back to some kind of restoration project, which I know some of the big companies don't do that, so it's kind of easy to find it out. But I think it is possible to enjoy the reef without completely ruining it. But you just have to make smart choices, I guess, and do research ahead of that.